looking at the two neodymium isotope systems that we have available to us. 147 samarium decays to 143 neodymium by alpha decay. Really long half-life. Whenever you hear about neodymium isotopes in geochemical literature, you generally hear mostly about 143 neodymium. But there's another short-lived radioactive isotope of samarium, 146 samarium, which also decays by alpha decay to 142 neodymium. And it has a half-life, it's about 1,400 times shorter. So all changes in 142 neodymium must have happened very early in the history of the solar system. Now here's the key thing. If the Earth is a C chondrite, then the Earth and chondrites must have the same samarium-neodymium ratio, and therefore the Earth and chondrites must have the same 143, 144, because we take this and we normalize it by 144. If Earth and chondrites have the same samarium-neodymium ratio, they must also have the same 142, 144. So what we want to do is compare the 142 neodymium isotope composition of chondrites in the Earth to see if they're the same to test this hypothesis. Yes. And non-radiogenic. Well, radiogenic, yes, but stable. Yeah.
Would you care to comment on that as it relates to the plot that Bill showed about diversity of neodymium isotopes in different chondrite classes?
There isn't a diversity of 143, 144 in different chondrite classes. There is a diversity of 142, 144 in chondrite classes, but O chondrites and C chondrites are 20 ppm depleted in depleted in 142 neodymium, and it's really close compositionally if you correct for nucleosynthetic additions, which I don't think Bill did. Now, E chondrites, some of them overlap with the composition of the Earth and some don't. But I'm going to open up the possibility here that the Earth doesn't have a carbonaceous or ordinary chondrite composition for samarium-neodymium. It wasn't a possibility until 7 years ago in terms of neodymium isotopes. Now it opens up Pandora's box. It's possible that chondrites have SMND that's 5-6% lower than the Earth. So just humor me here and let's see where this takes us and see if it solves any problems or creates more problems. So here's a fundamental paradox of helium and neodymium isotopes. This is a plot of ocean island basalt data, helium measured on glasses or olivines by crushing, and neodymium isotopes measured on these lavas as well. So here's the ocean island basalt database. Morbs plot over here. So depleted compositions are over on this side. Morb plots over here. Continental crust plots way over there, sort of beyond that wall in the other room. In this array, you'll notice that the highest helium-3,4 ratios, primitive ratios, don't correspond with primitive chondritic neodymium. This is a problem. One isotope system tells us that lavas with depleted neodymium isotopes at 5130 have primitive helium. But lavas with presumably primitive chondritic neodymium do not have primitive helium. So this decoupling of helium and neodymium isotopes has been the source of numerous papers where people try to propose how depleted neodymium can end up associated with the reservoir with primitive helium. Okay, so let's go back to the hypothesis we want to look at here. The standard model for the Earth is that the Earth and chondrites have the same samarium-neodymium ratio. So if the Earth has the same samarium-neodymium ratio as chondrites, then the Earth should have the same, if the Earth and chondrites are about the same age, the Earth and chondrites should have the same 143, 144 neodymium isotope ratio. This is also true for 142, 144. If the Earth and chondrites have the same samarium-neodymium ratio, be it 147, 144, or 146, 144, the Earth and chondrites should also have the same 142, 144. But then this discovery was made in 2005, which has made everybody's life a little bit more difficult. The discovery is that Boye and Carlson in 2005 found that modern terrestrial mantle-derived samples are shifted about 20 ppm higher than the chondrite classes. Now, there's a lot more data now, and now we know that enstatite chondrites plot either here or here. There's a whole spread of values for enstatite chondrites. Nonetheless, There is a group of, there are two groups of chondrites, O chondrites and C chondrites, that plot 20 ppm lower than 142, 144 relative to modern terrestrial samples. So what does this mean? Well, there are two hypotheses. This one I'm not going to explore today. Bill's talked about it. Rick talked about it. And it's that we simply have incomplete mixing of nucleosynthetic products in the in a solar nebula, so that Earth sampled a portion that had enrichment in 142 neodymium relative to the portion of the solar nebula sampled by chondrites. And I think the word is still out there, but I think the evidence suggests that nucleosynthetic processes that make excess 142, 144 aren't visible. The P process, for example, that would allow that to be true isn't observed in samarium isotopes, for example. So I'm not entirely convinced that poor mixing of nucleosynthetic products can explain this difference here. So I'm going to play around with this hypothesis that the 142 neodymium variation between Earth and chondrites is due to 146 samarium decay. It's not due to incomplete mixing of nucleosynthetic products. So what are the consequences of this? If this is true, if the Earth has higher samarium neodymium, a 146 samarium neodymium, than chondrites, then the Earth's also going to have high 147 samarium relative to chondrites. And this 20 ppm difference for 142 neodymium tells you what the difference for 143 neodymium is going to be. So for the geophysicists, just so you can see this process that I'm leading you through, just radiogenic growth and decay. This is how you make changes in 143, 144 over time. So this is your 147s decaying with 100 billion year half-life. And at 142 neodymium, the only thing that's different here is we have 142 instead of 143, and 146 here in the numerator decaying to 142 neodymium with a 68 million year half-life. So if you increase, 146, 147 samarium, as far as we can tell, is relatively constant in the early solar system. Therefore, if you increase 146 samarium to make this excess in 142 neodymium that we see in chondrites, that we see in the Earth relative to chondrites, then you must also increase 147 samarium, because the two are linked. Therefore, if 142 neodymium is 18 ppm higher in chondrites, in the Earth, relative to chondrites, then 143, 144 must also be higher, and by quite a bit. And how much higher is it? Well, it works out so that the range of values you get by increasing the samarium neodymium, 146 samarium, 144 neodymium ratio, by 5% to generate that 142 neodymium anomaly, also gives you a 143, 144 that's higher. So 142 neodymium increase also feeds back to 143 neodymium increase. And the value you get, it almost works out too well. This value now corresponds with the composition you find in the highest helium 3-4 lavas. Well, the question in my mind is this a paradox resolved? Now we have lavas with high helium 3-4 ratio that have primitive, but not chondritic, 143, 144. So where do we go from here? How do we get this increase in samarium neodymium and therefore increase in 143, 144 in the Earth relative to chondrites? Well, one idea, if you want to preserve the chondrite model, so the bulk silicate Earth is chondritic, what you have is chondrites here, the accessible Earth plotting here, and these would be the high helium 3-4 lavas with higher 143, 144 than chondrites. You also have to have a hidden enriched reservoir with low 143, 144, hidden somewhere in the Earth, that when added back together with the accessible reservoir gives you chondrites. But the key for this model to work is that this reservoir exists in the Earth. Well, this is also true for neodymium then too. The accessible Earth has higher 142, 144 than chondrites. This is the Boyer and Carlson discovery, which, if you want to preserve the chondrite model, requires you have a hidden reservoir in the Earth down here. So this, added together with this, makes chondrites. And there are problems with hiding reservoirs in the mantle. This hidden reservoir would have had to have formed before the giant impact. And the problem in my mind is how to keep the reservoir completely hidden during the giant impact. It seems like at least some of it would have been exposed in shallow reservoirs on Earth, or maybe even on the moon. But we don't see any evidence of it. Now, the other issue that I have is that this hidden enriched reservoir is going to have something close to half of the radiogenic heat-producing elements in the Earth. It's enriched, therefore it's enriched in uranium, thorium, potassium. So then, if we believe in plumes, it's really likely to participate in the plume generation process. So how do you keep this hidden for all of geologic time? You know, I spent a lot of time at Carnegie with Rick. I like to think I wasn't wasting my time completely measuring the same 142-144 ratio in hotspot lavas, hoping to find evidence of this reservoir. Didn't see it. Now, I can't say it doesn't exist, but after all those months, I'm not convinced that it does. So on vacation in Montana, we going to the family cabin, and we drove by Townsend, Montana, and I just saw this sign here, and it's kind of this moment. I realized we're never really going to know the answer about the bulk composition of the Earth until we actually dig down there, and I think Stevenson here has an idea how to do that. So now the question is, do we have an alternative? So what if we take away this hidden enriched reservoir? What are we left with? Well, the Earth doesn't balance with chondrites anymore, so we have to give up the chondrite model. Well, there's some momentum in this direction. Now, keep in mind that these papers have been published in Nature. The problem is Nature doesn't always get it right. People forget about this paper. I just want to remind everyone that just because it's in Nature doesn't mean it's spot on. So let's give up this hidden reservoir. We have the exact same plots now, but I drew a little white box and tried to make a line over it to get rid of the hidden reservoir. Now we have your chondrites and the non-chondritic Earth for 142 neodymium and 143 neodymium. And this 143 neodymium value happens to be the value that we find in high helium 3-4 lavas. I think that's interesting because high helium 3-4 is a noble gas signature that we associate with primitive early formed reservoirs. And look at that neodymium isotope ratio that we measure in these kind of lavas is also the ratio you'd predict given the 142 neodymium difference between Earth and chondrites. So it's really nice, and you don't need to bend over backwards to keep any reservoirs hidden. Well, the question is, well, okay, so this reservoir here is either a portion of non-chondritic primitive mantle that somehow survived for eons, or this reservoir is the depleted portion of an early depleted reservoir, and there's a hidden enriched reservoir down here that we've never seen. I can't tell you which one it is, but it's neat then that this early formed reservoir has the right neodymium isotope ratio to be consistent with primitive high helium 3-4.
You have to take magma ocean and crystallize it, and then remelt it to make this depleted reservoir.
Yeah, but very early on. That's right. You have to skim off some crust and either blast it off into space or put it at the bottom of the mantle. Either way, it's hidden from us now.
But first you crystallize the magma ocean, then remelt it.
Not clear what order that happens in. So maybe you crystallize, the portion that crystallizes out is enriched, and then you blast that off. Not clear. That's a question that could be explored. It has been explored. So you guys are probably mostly familiar with Stan Hart's model for FOSO, where you have these various mantle M members and multiple isotope space. Doesn't matter what isotope, you could X, Y, and Z, okay? But the point is when you measure these three isotopes on a rock and plot it up in 3 dimensions, you find that individual hotspots plot on these worm arrays. And the worm arrays converge onto a common region, which is Stan called the focus zone, or FOSO. Sounds like bozo. Now, FOSO has high helium 3-4, so lavas that plot down here have high helium 3-4, and they also converge on a common neodymium isotope ratio of, guess what? 5130. That's the value you find in high helium 3-4 lavas. So this common component in the mantle also happens to be a component that has the isotope characteristics with a primitive but non-chondritic terrestrial mantle reservoir. So if bulk silicate Earth isn't chondritic, my bet is that FOSO is what primitive mantle is.
When we find high 3-4 ratios in FOSO, do they kind of migrate up the arrays as well?
So some of these mixing lines are hyperbolic. Samoa, for example, which I know best, everything plots here, all the high 3-4 lavas. In Hawaii, the highest 3-4 lavas plot here. In Galapagos, they plot down here. In general, as far as I know, I've never come across everything out here is low 3-4, everything up here is low 3-4. And Pitcairn, the only sample that has relatively high 3-4 is right down at the tip, down here somewhere. I'm not sure if, yeah, there's the Pitcairn. It's right down here at the tip. That's a neat observation. And it's consistent with this 142 neodymium isotope discovery for the 143 neodymium that's predicted for a non-chondritic primitive mammal. Which one? The non-chondritic one? Well, okay, so see, you're catching me red-handed here. Everybody has their favorite place for FOSO. Mine would be over here somewhere, which is closer to the lead isotope value that you find in the lavas with the highest helium 3-4 values. Eric Howray drew a really big box. Hainan and Graham put theirs over here somewhere. But otherwise, the chondritic bulk silicate earth plots up closer to EM1, sort of up in this direction. The non-chondritic one is down in this direction. So here's the second part. So maybe I've convinced you, maybe I haven't convinced you that some obscure isotope ratios of some even more obscure trace elements might be consistent with a non-chondritic composition for the Earth. But then the big question remains, well, what about all the other elements? Forget isotopes. If the Earth isn't chondritic, well, what can we then say about the trace element or major element composition of the Earth? Because all the models previously have been based on using the composition of chondrites or the chondritic arrays intercept with peridotite arrays. But if we give up chondrites, well, do we give up knowing anything about the Earth? Personally, I don't want to jump off the chondrite ship and start swimming until there's another ship I can swim to. So here's where I'm going to try to build another ship, and you guys can burn it down if you want. But it's just, let me throw out this idea. So this new composition depends fundamentally on the 142, 144 difference between Earth and chondrites. The fundamental assumption of the model is that the SMND of the Earth is 6% higher than chondrites to explain why the Earth has 142, 144, 20 ppm higher than chondrites. And then you end up with a non-chondritic bulk silicate Earth composition that has isotope compositions like FOSO. So we have these we have one trace element ratio and a bunch of isotopes that we can rely on to construct this new composition for the Earth. So I'm going to use a lot of the assumptions that are used in the chondrite model, such as the neodymium-strontium isotope plot, which has been historically used to get the strontium isotope composition for the bulk Earth. Now, you measure chondrites. Bill pointed this out. The strontium isotope composition of chondrites is incredibly high, way out there. Not something you commonly see on Earth, maybe in continental crustal materials, really old continental crustal materials. So chondrites aren't a great way to get the strontium isotope composition of the Earth. But we do think we know the neodymium isotope composition of the Earth. And if it's chondritic, we assume that where the neodymium isotope composition of chondrites intersects the ocean island basalt and morb array is where you get the strontium isotope composition of the Earth. And knowing the age of this reservoir, age of the Earth, and the strontium isotope composition, and the initial value being the initial for the solar system, you get your rubidium strontium for bulk Earth. But if bulk Earth is now 5130, that also means that the strontium isotope ratio has to be lower, which means that the rubidium strontium ratio is lower to generate a lower value over 4.5 billion years. So in this non-chondritic reference frame, the RBSR of bulk silicate Earth is 30% lower of the chondrite model. The new model is 30% lower than the chondrite model. So now we have SMND and RBSR. Lutetium hafnium, you play the same game. Where does chondrite intersect with a global YB array, and you read off your favorite hafnium isotope value? Well, now if we're at epsilon neodymium plus 7 or 8, or 5130, 143, 144, then you get a higher 176, 177 hafnium ratio. And then, given that, the age of the Earth, an initial value for the solar system, you get a lutetium hafnium ratio For BSE, that's 12% higher in the new model. So now we have three parent-daughter ratios and a bunch of isotopes that we can now use to constrain the composition of the Earth. Yeah?
Aren't lutetium and hafnium, correct me if I'm wrong, aren't they both also refractory lithophile?
They are. So whatever messed up samarium and neodymium also messed up lutetium and hafnium. That's absolutely right. So notice I haven't plotted concentrations here, but I'm normalizing the sample to the McDonough and Son value as a reference frame, just so you see what my model looks like. So now you have three parent-daughter ratios, rubidium, strontium. So rubidium is now lower in the bulk in the new model relative to the chondrite model, which would be up here. The samarium-neodymium ratio is in the Earth is a little bit higher. So let's see here, samarium-neodymium, the samarium-neodymium ratio is a bit higher. Also, the lutetium-hafnium ratio is a bit higher. You have three sections of the spidergram that are floating around in space. You link them together with canonical ratios. What do I mean by canonical ratios? Ratios like strontium-neodymium that are very similar in continental crust and the depleted Morb mantle. So the idea is that you extract continental crust from a primitive mantle to make the depleted Morb mantle. And if continental crust and the depleted Morb mantle have the same ratio, that means that this ratio reflects the initial primitive reservoir in the Earth. And you have a couple ratios that are generally not very fractionated, like samarium, hafnium, strontium, neodymium, which you can use to link these three sections of the spidergram together. So now we have what I call the backbone of the trace element pattern for a non-chondritic Earth. Now you'll notice it's missing some key elements like uranium, thorium, and potassium. It'd be really nice to put those in. It'd be nice to splice in the rest of the rare earths. We have lutetium, samarium, and neodymium. So first, let's splice in the rare earths. I can tell you how I did this later. This is the one thing I did that I think annoyed Bill the least. Okay, okay. There are other canonical ratios you use. Barium, rubidium is pretty similar in continental crust and depleted mantle. Zirconium, hafnium is very similar. Again, these ratios must somehow reflect the original bulk Earth composition because the two most differentiated bodies, DMM and continental crust, have the same ratios. They're very similar ratios. Bill, I haven't inserted your favorite ratio here yet. Titanium, gadolinium, also very little fractionated. Now this is the hard part. Thorium, uranium, potassium, lead, and niobium. I'm going to tell you I punt on niobium right now. It's a big problem. It's a problem for everybody, no matter what model you buy into. If you buy into a chondritic mantle, there's a deficit of niobium in the Earth, and no one really knows where it is. So I'm not going to belabor niobium. But how do I splice these other trace elements into a spidergram for the Earth? Well, it turns out Bill showed me that barium, thorium, and continental crust is pretty constant and quite similar to the barium-thorium ratio you find in oceanic lavas. So again, it's another one of these sort of canonical ratios. So a barium-thorium ratio of 75 lets you put thorium into the spidergram. Again, notice I haven't given you any absolute concentrations. I'm just giving you a shape that's floating. This whole thing can move up and down. Then thorium, uranium you can get from isotope constraints, 3.9, just kappa. Just by using lead isotopes. And then once you have uranium, you can splice in potassium. Because potassium and uranium doesn't show as much variability in the Earth as some other ratios. It's not a perfect canonical ratio, but there are some pretty decent limits in the potassium-uranium ratio for ocean island basalts, for example. And I take a range of values for different reservoirs that, for example, Arevalo et al. Looked at. And they give you this range of potassium. This range of potassium-uranium ratios gives you this sort of range of normalized potassium abundances. Oh, I forgot. Uranium over lead. We know if this is the age of the Earth, it has to be on the geochron. So therefore, you know the uranium-lead ratio, so you can splice lead in there. I'm not going to talk about niobium because I don't know the answer. The neat thing about this is, well, what we need to do is figure out where to place this vertically. That's the big problem. So you have to adopt a model for how this this non-chondritic primitive mantle reservoir formed? Well, if we assume that it started off as chondritic but underwent a differentiation process, and that early melt was either lost in space or buried at the bottom of the mantle, then this can't be any more enriched than the McDonough's chondrite model. And lutetium is the least incompatible element. And so, in fact, lutetium varies very little in the depleted mantle. So we're going to put lutetium here. We're just going to pin it to chondrite. And that's the absolute highest. That's the absolute most enriched your pattern can be. What's the most depleted your pattern can be? Well, it can't be any more depleted than the depleted mantle. Now, there are independent estimates for the depleted mantle that melts to form morbs. Workman and Hart had their favorite, Salters and Strachey, Boyer and Carlson. And so what I do is I pin my estimate to the lowest, the most depleted DMM estimate out there. So that gives us our upper range and our lower range now for non-chondritic bulk silicate earth. And it's, it's between maybe 0.55 and 0.6 normalized to a McDonough & Sons primitive mantle. So not a huge amount of variability. It's pretty nice. Now, what can we do with this? Can we solve any problems? Well, if the potassium of the earth isn't here, which is where it would be for a chondritic sort of model for the earth, then potassium is going to be bound up in one of these upper or lower limits. And the cool thing here is that this might help us get a solution to the missing argon on the earth. It turns out that the potassium from the chondrite model couldn't be balanced by all the argon we observe in DMM, continental crust, and the atmosphere, so it required some missing hidden argon reservoir in the earth. But if we just assume that the whole mantle has the argon that we observe in continental crust, DMM, and the atmosphere, and there is no hidden reservoir, then you only need 155 to 205 ppm potassium in the earth. Well, guess what? This non-chondritic primitive mantle gives us between 145 and 200 ppm potassium. No need for a hidden reservoir, no missing argon. Well, also, if you're starting off with a pattern that's more depleted than chondrites, right here, so this would be the chondrite model. This is a line of 1 going across here. You're starting off with a depleted pattern. How do you pull out continental crust, which is really enriched, from a mantle that's already depleted? Well, instead of depleting all the way down to 660, the depleted upper mantle, you have to deplete at least 80% of the mantle to generate continental crust. So this requires that almost the entire mantle has participated in continental crust extraction. So people that advocate an early layered mantle, that's completely impossible with the new non-chondritic reference frame, if indeed it works. Thermal budgets, that's the biggest problem. I don't want to talk about that right now. I'll leave you with this. Mark Jelinek is working on that aspect of the problem. So basically, we have a really low URI number on the order of about 0.2. For comparison, McDonough & Son values about 0.3, maybe slightly above 0.3. And so you need a lot more primordial heat in the earth. There are some folks that think you can do that without ending up with a thermal catastrophe, but I think Bruce has been giving me some bad news that that's probably, well, we need to work on that. So anyway, thank you very much for your time.
Another corollary to this new trace element pattern, that there's actually no gas-rich argon-bearing reservoir in the mantle as far as we can determine based on the bulk locator potassium content.
Well, I can't say it doesn't exist, but the only reason we've come up with it is because you needed it to satisfy a chondrite model. But I'm telling you, with a different model, you don't need a missing argon reservoir. Hey, maybe it's there, but we don't need it.
But if a 534 source is a gas-rich or no gas-rich reservoir, there can't be that much argon in the reservoir, else you would be able to determine from your pattern right here, right? In my model, I consider this reservoir to be the most gas-rich reservoir. This would be the most primitive thing in the earth. But you already have all the argon accounted for produced by that pattern.
That's right.
Going through our atmosphere dealing with kind of crust. So
that's right.
You can't summon another reservoir.
You certainly don't need to.
So then the total number of atoms of argon in the 534 source has to be relatively
You can figure that out because we know the helium-3. We think we know the helium-3-4 ratio of that reservoir. So you could bootstrap that into the helium-argon ratio of maybe morbs and work from there.
How does this relate to what we heard this morning from Sujoy about hidden reservoirs for this analysis of nodal gas?
Well, I think that this is the reservoir that has the anomalous 129-130 xenon ratio that's different per morb that Sujoy is measuring in these high helium-3-4 isolate lavas. I think it's great.
Could you comment further on the radiogenic heat production and the thermal evolution?
You're not going to let me off that easy, huh? So yeah, I think someone said, maybe Bill, you put your hands on the surface of the Earth and you measure 46 terawatts of power coming out. In the standard model, McDonough's Son, 20 terawatts of that's radiogenic heat. In this new model, where you have maybe 35, 40% depletion in uranium, thorium, potassium relative to the standard model, 12 or 13 terawatts of that's radiogenic heat. So you have a lower Urey number. 0.2. So the question, so that requires that the amount of heat coming out of the surface, more of that has to be primordial. And the big problem is how do you avoid an early thermal catastrophe on the Earth? Well, there are a couple of different models. I don't know if any of these are right. Jun Kornaga has a nice little model that lets you get down the Urey numbers of 0.15. He seems to think that the Earth can tolerate this without having a thermal catastrophe. Crowley doesn't go to quite as low of Urey numbers, but suggests that dehydration of the Earth by melting is going to increase the viscosity of the mantle and slow convection, and therefore slow heat loss. And Rick has told me he doesn't think it would be a problem to take the Urey number down to 0.2. So, I mean, but these are models. I don't know how accurately they represent the reality of Earth convection and heat loss. Sure, Mark? Sorry.
What's the average age of radiogenic heat that's being sensed at the Earth's surface?
Good question. I don't know the answer to that, but there are some people in the room that...
Millions or maybe a billion years or something. So really, it's not a fair comparison to take the present radiogenic heat and compare it with what's coming out of the surface.
Well,
They should scale it to some time in the past that's more characteristic.
so that's the question. What's more characteristic? Is Van Kecken has this thermal model that shows that the Earth is in a period of maybe anomalously high radiogenic output. And he shows a plot showing incredible spikes in the thermal output of the Earth over time. And where we are there, who knows? Maybe we are into some transient 46 terawatts, and 500 million years from now, it'll be a heck of a lot lower than that, and it doesn't necessarily correspond with the amount of heat that was generated by uranium, thorium, potassium over that time interval. Good question, but I think as a dynamicist, Van Kecken struggles with that.